In our previous session, we had discussed about longitudinal static stability. Now let us start off with the lateral static stability. An aeroplane possesses static roll stability or lateral stability if a restoring moment is developed when it is disturbed from a wing level altitude. The restoring rolling moment can be shown to be a function of the side slip angle beta. The requirement for stability is that CL beta should be less than 0. The roll moment created on the aeroplane when it starts to side slip depends on the wing dihedral, wing sweep, position of the wing on fuselage, and the vertical tail. The major contributor to CL beta is the wing dihedral angle gamma. The dihedral angle is defined as the span-wise inclination of the wing with respect to the horizontal. If the wing tip is higher than the root section, then the dihedral angle is positive. If the wing tip is lower than the root section, then the dihedral angle is negative. A negative dihedral angle is commonly called anhedral. When an aeroplane is disturbed from a wing level altitude, it will begin to side slip. Once the aeroplane starts to side slip, a component of a relative wind is directed towards the side of the aeroplane. The leading wing experiences an increased angle of attack and consequently an increase in lift. The trailing wing experiences the opposite effect. The net result is a rolling moment that tries to bring the wing back to wing level altitude. This restoring moment is referred to as dihedral effect. The fuselage contribution to dihedral effect is also seen here. The sideward flow turns in the vicinity of the fuselage and creates a local change in wing angle of attack at the inboard wing section. For a low wing position, the fuselage contributes a negative dihedral effect. The high wing produces a positive dihedral effect. To maintain the same CL beta, a low wing aircraft will require a considerably greater wing dihedral than a high wing configuration. The horizontal wing also can contribute to the dihedral effect in a manner similar to the wing. However, owing the size of the horizontal tail with respect to the wing, its contribution is usually small. The contribution to dihedral effect from the vertical tail is produced by the side force of the tail due to side slip. The side force on the vertical tail produces both a yawing moment and a rolling moment. The rolling moment occurs because the center of pressure of the vertical tail is located above the aircraft's center of gravity. The rolling moment produced by a vertical tail tends to bring the aircraft back to a level altitude. In addition to lift created on the downward moving wing is created by the change in angle of attack produced by the side slipping motion. If we resolve the side slip velocity component into component along the normal to the wingspan, the local change in angle of attack can be estimated as delta alpha is equals to Vn by U, where Vn is equals to V sine gamma. The approximate side slip angle is beta is equals to V by U, but Vn is equals to V gamma. Assuming that gamma is small angle, the change of angle can be written as delta alpha is equals to beta gamma. Here on the left wing we have delta alpha 1 is equals to beta gamma and delta alpha 2 is equals to minus beta gamma, which says the angle of attack on the upward moving wing will be decreased by the same amount. The sweep angle also contributes to the dihedral effect. In swept back wing, the windward wing has an effective decrease in sweep angle and the trailing wing experiences an effective increase in sweep angle. For a given angle of attack, a decrease in sweep back angle will result in a higher lift coefficient. Therefore, the upper wing will experience more lift than the trailing wing. It can be concluded that sweep back adds to the dihedral effect. On the other hand, sweep forward will decrease the effective dihedral effect. I hope you would have understood lateral stability. Let us move on to directional stability in the next session. Thank you.